Welcome to your AP Statistics Chapter 10 video. Because we've done things in a different order, this is your last chapter to have a video over, so that's kind of exciting. We're going to talk about re-expressing data. Get it straight. We cannot use a linear model unless the relationship between the two variables is linear. Often, re-expressing can save the day, straightening bent relationships so that we can fit and use a simple linear model. Two simple ways to re-express data are with logarithms and with reciprocals. Re-expressions can be seen in everyday life. Everybody does it. The relationship between fuel efficiency in miles per gallon and weight in pounds for late model cars looks fairly linear at first. But a residual plot shows the problem. You can clearly see that there is a bend in these data. We can re-express fuel efficiency as gallons per mile, a reciprocal, and eliminate the bend in the original scatter plot. A look at the residual plot for the new model seems more reasonable. It looks more like a randomized cloud. There are a couple of different goals for re-expression. One is to make a distribution of a single variable, as seen in a histogram, more symmetric. So here we've got assets and hundreds of thousands of dollars and numbers of companies that have those assets, clearly skewed to the right there. Okay, but if we do the common log of assets, the distribution becomes much more symmetric. Goal number 2 might be to make the spread of several groups as seen in side-by-side box plots more alike, even if their centers differ. Their shape might become more the same, their spread might become more similar. Now, note this is a different goal. You don't have both of these goals necessarily for this same situation. Okay, these are different, they're almost like different reasons for re-expressing your data. Part of why we waited until now to do this is because I wanted to really get through linear, even inference with linear data before we talked about this. Another reason for doing the re-expression is to make the form of a scatter plot more linear, just like we saw with the example earlier. Here you can see. And goal 4 might be to make the scatter and a scatter plot spread out evenly rather than thickening at one end. So you can see that that happens here. This goal can be seen in the two scatter plots we just saw with goal 3. You can see that not only does it make the form more linear, it makes the scatter more even. All right, so how do you know how to do the re-expressions? Most of the time, we'll be working with logarithms, but that's certainly not the only type of re-expression you can do. There is a family of simple re-expressions that move data toward our goals in a consistent way. This collection of re-expressions is called the ladder of powers. The ladder of powers orders the effects that the re-expressions can have on data. Okay. So here we go. One rung of the ladder is 2, and that's where you square the data values. And you might try this with unimodal distributions that are skewed to the left, and you're trying to get them to be more symmetric. So you're looking at a unimodal distribution, so not a bimodal distribution. So this wouldn't be trying to linearize data. It would be more trying to get a symmetric histogram. A power of 1 is the raw data. You raise something to the first power, you just get what you started with. Data with positive and negative values and no bounds are less likely to benefit from re-expression, so you just want to leave the data alone. The power of a half, square root of the data values. Counts often benefit from a square root re-expression, so if you're working with counts, this might be something that's helpful for you for getting a more symmetric distribution. Again, we're not really doing bimodal or bivariate data here. For 0, we'll use logarithms here. Measurements that cannot be negative often benefit from log re-expression. Many times when we're trying to linearize something, working with logarithms is helpful, and we'll get into that more in a minute. A power of -1/2 is the reciprocal square root, an uncommon re-expression, but sometimes useful. -1 is the reciprocal of the data. Remember, an exponent, a power of -1 just means use the reciprocal. Ratios of two quantities, in other words, like miles per hour, often benefit from a reciprocal. So if you don't like what you see in the original expression, try doing the reciprocal. Try raising it to the -1 power, and you may find when you do that, you get a more linear set of data. So remember, you've got different goals. So when it talks about like try with unimodal distributions, for unimodal distributions, that implies that you're looking at modes. So you're looking at, say, a histogram, so univariate data. And so in that case, you might try squaring. Okay, so any of these can be useful for getting a different form. Attack of the logarithms, and this is going to be really helpful whenever you are working with bivariate data. When none of the data values is 0 or negative, logarithms can be a helpful ally in this search for a useful model. Also remember, the reciprocal works sometimes. You really can't rule any of them out completely, but logarithms can be very helpful here. Try taking the common logs of both the x and y variable, or you can do natural log if you'd rather do that. Then re-express the data using some combination of x, or common log of x, versus y, or common log of y. Okay, the model between x and y is exponential if you've got x, the plain x's on the x-axis, and the common logs of y on the y-axis. This model is for the 0 power in the ladder approach, useful for values that grow by percentage increases. You can also have a logarithmic relationship between x and y, and that's going to be when you get something that looks linear, when you have the common log of x on your x-axis and plain y on your y-axis. A wide range of y values, or a scatter plot descending rapidly at the left but leveling off toward the right may benefit from trying this model. Okay, if it looks, logarithmic, try doing this. A power model, this is if there's a power relationship between x and y themselves, that means you're going to have a linear relationship between common log of x, common log of y. Sometimes this is called the Goldilocks model, when one of the ladder's powers is too big and the next is too small. This one may just be perfect for you. We often choose a re-expression for one reason and then discover that it has helped other aspects of an analysis. For example, a re-expression that makes a histogram more symmetric might also straighten a scatter plot or stabilize variance. Okay, so if you're looking at a single, just one of the variables, and you're looking at its histogram, and you're like, ooh, I need to do this re-expression to make it more symmetric, you may find that when you plot it against another variable, you have a better linear model, or you may stabilize the variance. Why not just use a curve? If there's a curve in the scatter plot, why not just fit a curve to the data? Well, the mathematics and calculations for curves of best fit are considerably more difficult than lines of best fit. Besides, straight lines are easy to understand. We know how to think about the slope and the y-intercept. So what can go wrong? Don't expect your model to be perfect. Also, don't stray too far away from the ladder. If you're finding yourself taking the 5th root or something, or raising something to the 5th power, that really goes beyond the scope of this course, and so that's not going to be something that we necessarily want to do. Don't choose a model based on r squared alone. If we're talking about r and r squared, we are stating that we've already looked at the scatter plot, and what we have is a linear relationship. So you want to make sure you're looking at scatter plots when you're choosing your models. Beware of multiple modes. So when you're looking at one variable at a time, multiple modes, 2 or more peaks, we can't necessarily do a re-expression that are going to pull those several modes together to give you a nice bell-shaped symmetric distribution. Watch out for scatter plots that turn around. Re-expression can straighten many bent relationships. Okay, so if we have a nice little dip like this, or a little peak like that in our linear relationship, but when you have valleys and peaks, when they curve more than once, we're really not going to be able to straighten those out. You need more complicated models that go beyond the scope of this course. Watch out for negative data values. It's impossible to express negative values by any power that is not a whole number on the ladder of powers, or to re-express values that are 0 for negative powers. So just be careful with that. Watch out for data far away from 1. And so data values that are all very far from 1 may not be much affected by re-expression unless the range is also very large. If all the data values are large, in other words like years, consider subtracting a constant that bring them back near 1. Okay, let's look at the step-by-step problem on pages 229 to 230. They're based on some data from page 149, so I, instead of having you look for it, decided to just go ahead and put it here in a table. You need to open a new document with a spreadsheet page and enter the data that I'm giving you into the first 2 columns. And you need to name the first column something like years, and the second column tuition. Anything that the calculator will accept and that's meaningful to you will be fine. So we're looking at years since 1990. So we're looking at 1990, 91, 92, 93, 94, 95, 96, 97, 98, 99, and 2000. And we're looking at tuition. Make a third list, common log of tuition, if you want to go back. If before you do that, you want to go ahead and insert a second page and look at this scatter plot just between years and tuition and verify that it's not really a linear model. Now go back to your spreadsheet page, and please feel like you can pause me and go work on this and then come back. Make a third list, common log of your tuition. Okay. Now go back to that second page of your document, make a scatter plot of years and the common log of tuition, and confirm that it is straight enough. Okay, that it's a reasonably linear model. Okay, now on this spreadsheet page where you have your list, do linear regression for years and common log of tuition. Okay, so your linear model. Now the calculator isn't going to realize that you did the common log of your y value, so it won't know that really your model is between x and the common log of y hat. That's something you have to bring to the situation. You have to know that you're looking at the linear relationship between x and common log of y hat. And so this means the relationship between x and y is exponential. If both are logs, then the underlying relationship is a power relationship between x and y. If you have just y hat and you are looking and plugging in common logs of your x's, that's a logarithmic relationship. Okay, let's predict the 2001 tuition. So first thing we need to do is figure out what x is. So 2001 minus 1990 is 11. So we're going to plug that into our equation, and we get that the common log of y hat is approximately 4. So take that common log of y hat equals 4 and write it in exponential form. So that means you're going to do the 10 to the 4th equals y hat, or y hat equals 10 to the 4th. Okay, remember this is logarithmic form. And so to write it in exponential form, you use your base, which is an understood 10, and raise it to the 4, and that's going to equal y hat. So our predicted tuition value for 2011 is $10,000. Okay. All right. Okay, you're going to get a chance to work with some data that are nonlinear and to be able to transform them and then make a prediction and get back to y hat, even if there's been some sort of transformation done. For your linear model, you'll do the inverse transformation to get to your actual predicted y value. Alrighty, I will see you in class. Have a good day.